Bismillahirrahmanirrahim. For heavy engineers wherever you are, now I would like to share about the compression member designs that was accorded into American Institute of Steel Construction 2016 as a part of civil engineering workshops on August 21. Let's enjoy this. We have three topics for our discussions about the compressions member designs. They are structure analysis, structures modeling, and design and analysis of the compressions member designs that was accorded into AISC 2016. As long as we know, in steel structures analysis, we had two types of loads that were carried on in the steel truss structure system. They are tension and compression load. The compression load can be caused by the gravity load and or the environmental load such as the wind loads. Usually, the compression load had been presented in a negative value that showed that the load was carried on toward to the cross sections of the member. Similarly, in the tension load member design, in the compression load member design, we have load analysis that was consisted at least at three types of load cases. There are dead load, leave load, and the wind load case. The dead load have been consisted and three components of the dead load. There are shaft widths, purlins loads, roof covering, and connection loads. The connection loads usually takes 10% of the summarize of shaft width, purlins, and roof covering loads. The leaf load usually takes 100 kg force or equal 1 kilonewtons. And the wind loads was considered into type of the wind loads according into the wind directions. There are right wind and the left wind. Both of them was consisted into type, the windward and the leeward wind load. Now we want to discuss about the load combinations that was occurred in the compression load member design. The load combinations had been considered in this case was accorded into two types of the design criteria. There are a level strength design AISD and the load resistance factor designs or LRFD. Of course, you should take the largest compression loads that you can find then from your structures analysis by utilizing sub 2000s maybe or any else. And once make it sure that the member or the cord has been satisfied for the load compressions. The basic principle of the compression member design that the nominal compression load should be larger than the actual load for the allowable strength design and larger than the ultimate compression load for the load resistance factor designs. Okay, and of course the nominal compression load should be reduced by a factor that we can discuss it later. In the compression member design, we had the general equations for calculating the nominal compression load. The nominal compression load can be computed by multiplying the critical stress and the cross sections area of the steel profile. We have the type of design criteria. They are level strength design and load resistance factor design. I said that the nominal compression load should be reduced by a factor. For AISD, we can divide the nominal compression loads by 1.67 for a level strength designs. And for load resistance factor design, we can multiply the nominal compression load with 0.9. Now we have questions how to determine the critical stress. The critical stress can be determined by distinguishing them in inelastic or elastic compression member. How can you identify them? When the slenderness ratio or KL per R is less than 4.71 square roots the modulus of elasticity per the yielding stress, the critical stress can be computed by 0.658 to power of the yielding stress per the Euler stress. Then we can multiply it by the yielding stress. Conversely, when the slenderness ratio is larger than 4.71 square roots the modulus of elasticity per yielding stress, the critical stress can be computed by multiplying the Euler stress and 0.877. The keyword is inelastic or elastic case. How about the Euler stress? Simply, the Euler stress can be computed by dividing the Euler load and the cross sections of area. Or in another form, we can say T squared multiply the modulus of elasticity and divide it with the slenderness ratio in square. The next question was the Euler load. The Euler load, or in another name, we can say it, the critical load had been defined as the load that can cause the compression member getting buckled. Okay. The Sweden mathematicians Professor Leonhard Euler in 1757 have introduced the first equations for the critical load. The equations depend on the length effective, and the key showed that the boundary conditions coefficients. We talk about it in the next slide. The effective length or KL has been determined by considering the boundary conditions of the member. We're gonna look to find out the value of K. When the member had been constrained by simply supported or pin-pin supported, the K is 1. And when the member had been constrained by the fixed supported, the K is half. You can find the value of K on the AISC table. The effective length or KL has been determined by considering the boundary conditions of the member. We're gonna look to find out the value of K. There are some references can be used, maybe for strengthening your understanding in tension member designs, with the specification for structural steel buildings, American Institute Steel Constructions 20M16, the minimum design notes for buildings and other structures by American Society Civil Engineering, and the Mr. Seeger's book, Steel Design, in the 5th editions. Finally, thank you very much for supporting NIPL project channel. We would like to serve you in structure analysis tutorial, finite element analysis tutorial, research partnerships, training and development in engineering paper, thesis, dissertation, design analysis, and forensic engineering consulting. Don't forget to subscribe this channel, like, and share. Thank you very much. See you. Assalamualaikum warahmatullahi wabarakatuh.